This is lecture 27 of Physics 210A. Thermal physics. And today I am going to talk about connection between the microstates of a system and its entropy. And this kind of introduces you to the idea of statistical mechanics. So, to begin with, let us state the principle of maximum entropy, and that is our system left to itself achieves equilibrium when its entropy is maximum. So that's the entropy principle. The question arises, can we show this from equations of motion, that is basically Newton's laws, or something more is needed for it? And the answer is that equations of motion cannot give the maximum entropy principle. And therefore, we have to learn about it by looking at the systems in a slightly different way. The connection actually entropy of a system is with the probability of it being in a microstate. So first I got to define microstate. What is a microstate? A microstate is a particular distribution of particles in a system and all microstates in system in equilibrium give the same macroscopic variables. So, a particular state would give you uniform distribution of particles in a given volume, temperature would be the same, and so on. But microstates could be different. Let us illustrate this with a simple example. Although it is not a statistically very large system, but nonetheless. So, the example would be distribute a number of particles in two chambers of a volume. So, what we are doing is we are taking a container with some volume V and dividing it into two partitions. Let us call it box 1, box 2. And I am taking some particles and seeing how they can be distributed. All those would be microstates. Now, the equilibrium situation is where the density of particles is uniform. That means the particles would be divided equally. So, let us see now, let us take number of particles to be 2. And divide them into these two boxes. Now, number of ways of dividing n particles with m in, let us say, left box and n minus m in the right box is n c m, and choose m, which is n factorial over m factorial m minus m factorial. What it is doing is counting the number of ways we can occupy these boxes by taking these n particles and then dividing by the permutations that can these m particles or n minus m particles can have. So, n factorial is the permutations of n particles, and then m factorial is permutations of m particles, and n minus m factorial is permutations of n minus m particles. So, let us take particles one by one. So, to start with, I am taking 2 particles. So, let us write the number of particles in the left box. Right box, and number of ways. Larger the number of ways, more the probability of this happening. So if I put in the left box 2 particles, 0 particles, this is exactly one way. If I take them to be 1, 1, this will be 2 ways. And if I take them to be 0, 2, this is again one way. And according to what we said, that uniform distribution is the equilibrium distribution, this is the equilibrium distribution. Now let's take more number of particles. Let's make it 4 particles. Let's take left box, right box, and number of ways. You have 4, 0, number of ways is exactly 1. 3, 1, number of ways is 4. 2, 2, number of ways is 6, and then the other way. You can have 1, 3, and 0, 4, 4, and 1. Again, this one is equilibrium state. You can continue doing this. Let me do one more with the number, and then I'll do it for n. So number of particles is equal to 8. And I have left box, right box, and number of ways. You have distribution 8, 0, one way, 7, 1, 8 ways, 6, 2, 28 ways, 5, 3, 56 ways, 4, 4, 70, then 3, 5, 56, 2, 6, 28, and so on. So again you see that the uniform distribution here is the one that has maximum number of states. Let's do it for n particles. For n particles, first I develop something called the Stirling approximation. And the Stirling approximation is that log of n factorial is equal to n log n minus n, which can be written as n log of n over e, and therefore I can write n factorial as n over e raised to n for large n. I like you to obtain this approximation by taking log of n factorial equals summation I equals 1 through n I, and changing the sum to an integral get Stirling's formula. So now let me do it for n particles. What I'll do is I'll do it for 2 or 3. So let's take left box, right box, number of ways. Let me take the uniform or equilibrium distribution to be again n by 2 and n by 2. Then consider some other distributions like n by 3 and 2n by 3 and n by 4 and 3n by 4. And you can go the other way also. And you will see that the number of ways is 2 raised to n here, 2 raised to n times 5.54 times 10 raised to minus 3 here, and 2 raised to n times 2.13 times 10 raised to minus 6 here. So now you see as n becomes large, this is for hundred particles. That's how you get this factor. Otherwise, this factor is, the factor in terms of n is 1.5 over 1.58 raised to n for n third, 2n third distribution, and 2 divided by 2.279 raised to n for n by 4 and 3n by 4 distribution. So you see, as number of particles becomes 100, again the maximum entropy, maximum number of states are for n by 2, and this is using a Stirling's formula. Now I want you to note that 2 raised to n is also the total number of ways n particles can be put in 2 boxes. So that means in equilibrium situation, the number of microstates is almost equal to the total number of microstates. So almost all the states have this inequilibrium distribution, the maximum possible states, and these are almost equal to the total number of microstates. Now we make a further hypothesis called the ergodicity, and what it means is that a system goes through all possible microstates. I mean, the macroscopic variables could be different. For these microstates. So, the probability of finding a system with a macro state is equal to number of microstates for that divided by total number of microstates. And this implies that in equilibrium, the system has very close to probability very close to 1 probability of being in such a macro state. And through all this, what we learned then is, or we conclude, is that entropy must be related to probability of being in microstates corresponding to equilibrium, because that's where the number of microstates or the probability is maximum, and so is entropy. So this is because both entropy and number of microstates for this is maximum. So entropy is related to probability of being in microstates corresponding to equilibrium, or equal to the number of, or related to the number of microstates in that. So what we are going to do is now write that the entropy S of a system for a given set of parameters is going to be equal to number of microstates, and these microstates are consistent with the macrostate being observed. And we are going to denote by omega whatever the variables, let's say u and v, equals the number of microstates for a given u and v. So, S is related to omega. S is related to omega. How is it related? For this, we will consider two systems. Consider two systems with number of microstates omega 1 and omega 2. Then omega total is going to be omega 1 times omega 2. But entropy is going to be S1 plus S2. So, this immediately implies, this gives you that S is proportional to log omega. Or we write, and after fitting and everything, that entropy is equal to K Boltzmann log omega. So, with this, now we can check how omega changes with temperature and energy. So, what we have concluded is that entropy of a system S equals K Boltzmann log of omega. Now, you see, I just want to comment here before going any further on multiplicity and disorder. Now, omega, consistent with, say, energy U, volume V, is the multiplicity of microstates corresponding to a macrostate. It is a number well defined, but disorder cannot be defined in a definite way and quantitatively. So, sometimes when people say that entropy is related to disorder, it is better to call it that entropy is related to multiplicity of the microstates corresponding to a macrostate. Now, let us find the relation between omega or the energy or U and E at a given temperature. So, consider large reservoir. A reservoir by definition is large. So, there is a reservoir at temperature T. So, it has this omega E. If I take the derivative of entropy with respect to its energy U, at constant volume and n. Then this would be equal to k b over omega log of omega u over du. Our log will not be there because now I have taken 1 over omega. So, this is du over d omega, and this immediately gives you that omega is equal to some constant e raised to u over kb t. Usually we write instead of u energy, so replace u by e and get omega e equals some constant e raised to e by kbt. I took a reservoir because by changing u I should not be changing the temperature much. So, we have gotten omega e equals some constant e raised to e over kbt, and this implies that omega e increases exponentially with e for a given temperature. So, if you increase the energy, number of states will become larger and larger exponentially. Something like if I were to plot omega e versus e, it will go very sharply up. So, with this knowledge, let us calculate now the probability that a small system with multiplicity omega e, which is countable, let us say 1, 2 or so on, very small number, in contact with a heat bath at temperature T. Has energy E. So, what we are considering is a heat bath, a reservoir, and a small system. Total energy is some E0, which is E of the reservoir plus E of the system. So, system has energy E and this has E reservoir. The number of microstates omega, let us call it E, when the system has energy E, will be given as omega reservoir E0 minus E times omega system E. Now, you see, when we plotted it earlier, we showed the omega. So, if I were to plot omega total E, it will be product of omega SE and omega reservoir E. Omega SE may be going up sharply, omega reservoir may be coming down sharply. So, you get a place where you have distribution of omega like this. It's all schematic. So you get things at equilibrium out here. How does that happen? I am taking omega e to be rising sharply. So this means that even the system in touch with reservoir is large, macroscopic, so that this temperature can be defined. Then I have omega E equals omega E0 minus E, omega E. And what is the energy of the system? That will be given by maximizing omega E. So when omega E is maximum, that will be the energy of the system. If I maximize it, what do you get? You take log of omega E, which will be log of omega reservoir E0 minus E plus log of omega system E. And you maximize log omega E. So when I take d by dE of log of omega E and put it equal to 0, I'm going to get d by dE with a minus sign log of omega reservoir E0 minus E. I can put this in the absolute terms, and plus d by dE of log of omega system E equals 0. Now we have taken system large enough, system is large enough so that little perturbation in the energy doesn't change the system much. So all these derivatives are taken at the equilibrium energy. So E equilibrium, this is also taken at E equilibrium. And this gives you 1 over T reservoir equals 1 over T system, provided the temperature can be defined. So we have taken large enough system, it's a macroscopic system, so T can be defined. So from this statistical point of view, what we are getting is at equilibrium, the temperature of reservoir and the system is equal. You could also think of it as two large systems, two large macroscopic systems is also okay. So this is what it is. At equilibrium, this is what happens. Now let's go back to the case of finding the probability if there is a very small system and what will be the probability of it having energy E. So now consider a very small system. So omega E is 1, 2, or so on. So this is, say, a system where T cannot be defined for the system. Because you take d omega E dE, you change E slightly and the system goes into, jumps from one to the other. For example, if there is a system with, say, like harmonic oscillator, E equals h nu, 2h nu, and so on. In that case, it will become very difficult to define temperature of the system. Now, if you take a reservoir at temperature T, and we are taking omega E to be equal to omega reservoir E0 minus E omega E. Now, it's a little bit of energy comes from reservoir to the system. Nothing much changes in the reservoir. So, I am going to write omega reservoir at E0 minus E. E is much less than E0. This can be written as omega reservoir E0 minus E dE d omega R dE at E0 plus higher levels. This I can write as omega reservoir E0 minus E over omega reservoir at E0 d by dE of log omega reservoir at E0. And this I can write as omega reservoir, sorry, this is denominator, this will be on the top, omega reservoir E0. Omega reservoir E0 minus omega reservoir E0 E over kBT. So, we are writing omega total E is equal to omega reservoir E0 minus E omega system E, and this is coming out to be omega reservoir E0 1 minus E over kBT, plus there could be higher order terms, which would be the series and omega S E. You can show that this series is exponential, so this can be written as omega R E0 e raised to minus E by kBT omega S E. Now, in case of small systems where omega S E is of the order of 1, 2, and so on, it is called degeneracy of the state. So, omega, and this is written as G. Let us say state is I with energy EI. So, I can write omega EI is equal to omega reservoir E0, which is the total energy, GI e raised to minus EI over kBT. This is a constant. So, omega EI is equal to some constant GI e raised to minus EI over kBT. Since summation I omega EI should be 1, the CI, the C constant, is going to be equal to 1 over summation GI e raised to minus EI or KBT. This is C. So, the probability is equal to GI e raised to minus EI over KBT divided by, this is known as the partition function Z. Z is equal to summation GI e raised to minus EI over KBT is equal to partition function. So, what we have given is that if there is a small system, microscopic system with some degeneracy, the probability of it being in some energy state is given by what is known as the now Boltzmann factor. So, what are the lessons that we have learnt? I gave these in my concluding remarks for this lecture. These are that the entropy of a system at some energy E is given as K Boltzmann log of omega E, where omega E is the number of microstates for system, and these are consistent with the macroscopic quantities. We have also learnt that there is a small system in touch, in contact with the reservoir at temperature T, and the probability of it having energy EI is proportional to its degeneracy for that energy state minus EI over KBT. With this, I stop here, and in the next short lecture, I'll apply these ideas to calculate entropy of an ideal gas. Thank you.